And I need a volunteer. Oh, you've already volunteered. I don't think you volunteered. Okay? I have two envelopes here. They're unsealed because due to the continuing budget crisis, if I seal them, I can't use the envelopes again. So. Okay?
So imagination.
Yeah, so pretend they're sealed. And in fact, one of them is slightly different than the other. So we can... Alright. So this is the two envelope problem. In one envelope, there's a certificate worth X dollars. In the other, 2X. Okay? How many of you have ever seen Deal or No Deal? This is almost at that level of intelligence required. Which envelope do you want? So I said, which briefcase? 7, go with 7, go with 7!
That is the correct.
I'll give you a +1. That is correct. And which envelope do you think has 2x? Let's refine the question. Good. As I said, you have to ask them, which one do you think? And the class can help you. They can say left or right. You guys can help. Which do you think?
I think it's a shell game.
Okay.
You want this one?
Yeah, sure.
Okay. Now don't open it. Don't look inside. Okay. Let's do some math first. Okay. This is a math class. Okay. Let's try to calculate your expected value. So what is your expected value? If you switch. So do you know how much is in your envelope?
No.
Okay. So let's say you have D dollars. Okay. What are the possibilities for the other envelope? 2D. And how often do you have 2D?
Half the time.
And what's the other possibility?
Half the.
Yeah, you don't want that. So, if you keep your envelope, what's your expected value?
D.
D. If you switch, the expected value is what?
D plus.
Don't do any algebraic simplifications.
Oh, okay. Half times 2D.
Yeah, I normally would write it 2D times a half. Doesn't matter.
Plus half times D over 2. D over 2 times half.
And what does that equal?
D plus D over 5D over 4.
So you chose the left?
Yeah.
Who said right? Do you really want the left? What's your expected value if you switch?
5D over 4.
So do you want to switch?
Yes.
Okay.
This is the goat problem.
This is like the
Monty Hall.
3 doors.
No, it's not the same as the 3 doors problem.
But,
It's not. The 3 doors, the trick is Monty Hall will never open up the door revealing the car.
Okay.
So that's the trick. If he truly opened the doors randomly, we can talk about this problem later. Alright, so she just switched. Alright, so let's do the analysis again. Let's say there's D dollars in your envelope. What are the possibilities for the other envelope?
5D over 4.
Who said left? Do you really want to keep that envelope? If you switch, you'll get 5D over 4.
Just give me both envelopes.
You're getting so
Tell
much
me when to
value.
stop and tell me when you want it.
so much fun.
Alright, so open it up and see what you got. And we actually just got an email that we're not supposed to print out so much I had to get special permission to print out this number.
God.
You're a really big number.
So what does it start with?
7.
Okay, it starts with 7. So it's about 7 times 10 to the 9,999, or 99,900, something like that. I think you did better. This one is only starting with 3. Yes, it's 3 times 10 to the 9,999. Yours is 7 times 10 to the 9,999. So you actually chose the correct envelope. Well done.
To actually get this much money?
Yes, so let me just give you an
Well, you don't know what the unit of currency is.
Well, so it says dollars.
Well,
Math$41. Worthless everywhere else.
they're like points on.
Okay, here you go. Now I do have a lot of trouble with reimbursements for my grants. We'll see if they will accept that. In fact, I had another trouble recently with a trip, so that has now become an exam question for you guys. What's wrong here? It shouldn't be in her best interest to keep switching time after time after time.
It's not 2D and D over 2, is it?
I'm sorry?
I mean, if you have D dollars, if your expected value is like 1.5x, then when you swap, it's not D over 2.
Well, the expected value is 5D over 4 if you switch. Half the time you'll have twice D, half the time you'll have half D.
Half D? Even though D's perfectly...
If you had 2x dollars and then you switch, then you went
Okay.
into that.
Right.
Okay, I see what you're saying.
So the difficulty here, and it's a really subtle paradox, is we're trying to put a uniform distribution in all the numbers. I can't choose all numbers equally likely. If I try to put a uniform distribution on the positive reals, that would integrate to infinity. So I have to have a distribution that's either truncated and uniform, or I have to have a distribution that decays. If the distribution decays, then the probability of these two events won't be equally likely. That's the subtlety here. And so what I was able to do using Mathematica this morning is I chose a number randomly, a random integer from 1 to 10 to the 1,000. Oh, no, I'm sorry, 10 to the 10,000. Mathematica can do something like that very easily. It looks like I'm choosing the number randomly all the way up to plus infinity, but I'm not. It's a very large finite interval. Okay, that's the subtlety here. So this is a nice way to use expected values, but this is a danger of making an implicit assumption when you're trying to use expected values. So this is one of the more famous problems or paradoxes in the subject. Okay. Alright, so for the next one, I want to do variances next, and then I'll give you your choice. I can either talk about the theory of convolutions, or in honor of today not being Mountain Day, I can talk to you about how to find a spouse. Right, how to use mathematics to find a spouse. Just, we can't share this video with my wife, okay? Very, very important. Hi, dear. Okay. Variances. So we've talked a little bit about variances before. And we're conjecturing, maybe if independent, the variance of the sum of AI xi is the sum of AI squared variance of xi. Say I goes from 1 to n. And we talked a lot about why a formula like this is reasonable. Now, one thing is when we're trying to figure out what the variance of the sum is, if I take all the a's to be 0 but the first term, then it's really easy. You know, if I take the first a to be 1 and everything else to be 0, then the variance of the sum has to just be the variance of x1. So whatever answer has to depend on the variance of each beast. We talked about, could we have just AI? No, we could end up having a variance that's negative. Could we have AI to an absolute value? No, that's going to give us the wrong units. It won't scale properly. This is the simplest thing that will work. Okay? And so a key ingredient in the proof is the following. If x and y are independent, that implies the expected value of x times y in your dream world. What would you want that to be? It would be
The expected value next time.
good, right? This is exactly what you want to hold. The expected value of a product is the product of the expected values. This is only true if they're independent. Well, I'm sorry. If they're independent, it's true. This can be true just coincidentally if they're not independent, but you can't count on it. Okay? It kind of makes sense. If x and y are independent, they don't really see each other. And so remember, here's the proof. If x and y are independent, then the probability density f xy factors as something in x times something in y. So if I have two independent random variables, the joint density function is just the product of each individual density function. So now, the expected value of xy is, I always like to do things over integrals rather than sums, is I integrate over the whole space, I take the value xy, and I multiply by the probability that I got xy. So this is how I would calculate the expected value of the product. So the first step should be clear. I tell you the joint probability function factors. Let's put that in. And so when I put that in, I go from minus infinity to infinity, minus infinity to infinity, xy, f of xx, f of y, y, dx, dy. And when you see algebra like this, it should be screaming at you to do something. What should you be doing here?
Joining like
I'm sorry, joining like terms, segregating, right? This is a situation where it's okay. And in fact, you're mathematically encouraged, okay, right? You want all the x's together, you want all the y's together. And when you do that, you have the integral from minus infinity to infinity, x, fx of x dx, integral minus infinity to infinity, y, fy of y dy. Well, the first integral is just the definition of the expected value of x. And the second integral is just the expected value of y. And so that's the proof. Yes?
Remind how you can just separate out, like, as then multiplied into two separate integrals rather than just...
So this is just results from Calc 3.
Okay.
That if I have an integral over here, what I can do is say, let's have x fixed, and now do the y integral.
Okay.
And x is a constant with respect to the y integral. I can just pull it out.
Okay. And then do the same thing.
And then do the same thing.
Okay.
What's the definition of independence for random variable?
So the definition for continuous things would be the joint density function would split like this.
That is the definition.
I'd say that's a good definition. And so over here, because they're independent, the joint density function splits. So knowledge of one gives you no information about knowledge of the other. Okay? In general, will we be able to do this? No, in general we won't be able to split things like this, and we'll have a more complicated double integral to do. So now that we have this, we can turn and we can look at what's going on for the variance problem, and we can solve it in the special case when all of the variables are independent. The difficulty is when we actually have some dependencies. So, proof of variance formula. As much fun as it is to keep writing out all the integrals, I'd like to be able to tell you how to find a spouse, so I'm going to go a little bit faster, and I'm going to just use the expected value symbol. It's a way of basically a nice shorthand notation of all the integrals together. So the variance of the sum of ai, xi, I goes from 1 to n. How would we calculate this? This is the expected value of the sum, I goes from 1 to n, of ai, xi, minus the sum, well, I'll do it very slow, minus the expected value of the sum, I goes from 1 to n, of ai, xi, squared. Right? This is the definition of the variance of something. To calculate the variance of a quantity, subtract its expected value, square, and take the expected value of that. The other thing I could have done is I could have said it's the expected value of the square of this minus the square of the expected value. I want to write it like this. So let mu I equal the expected value of xi. So really I'm just writing mu I for mu x of I. I don't want to have to write something as elaborate as this. And so now we get our expression is the same as the expected value of the sum, I goes from 1 to n, of ai, and let's just group together xi minus mu I lots of parentheses, squared. What we're doing is we're basically grouping, we're segregating as before. I have an xi here, I have an xi here. Let's put them together. And they're both being hit by ai, so we have something like this. Okay? So now we have to expand out the square. So when we expand out the square, we're going to be a little bit careful. So I have this thing and I multiply it by itself. Tell me if this is right. I have the sum I goes from 1 to n of ai xi minus mu I times the sum I goes from 1 to n of ai xi minus mu I. Is that correct? You know, I have this squared, so I just wrote it twice. Correct or not correct? I'm supposed to square it, so I multiply by itself, right? This is one of the most common mistakes in the subject. What did I do wrong? Yes?
The xi isn't occurring separately twice. So I don't know if that's relevant, but we don't have two different instances of a variable with the distribution of xi. We have one instance squared.
You're close.
You're squaring the individual terms, you're not squaring the entire sum.
No, I'm squaring the whole sum. I have the whole sum, and then I write the whole sum again. I've written the sum twice. I've done something wrong that's very subtle. Yes?
Are you supposed to have an AI on both sides? Or did you double
Or maybe everything is right.
include?
So is everything right? I technically have not made a mistake. I have just done a horrible abuse of notation.
Should you use I both?
I shouldn't use I both times. It's extremely confusing to use I both times. It's not wrong, right? I have this sum over I, and then I have this sum over I. But I could get very confused, and I could drop one of the sums. And if I drop one of the sums, I'm then saying the sum of the square of the sum is the sum of the squares, which is not the case. This is bad notation. What should I use? Right. Which is very nice to get from I. You just go down like this and loop it up, and you can easily turn i's to j's. All right. Now we have much better notation. Okay. So again, it's not necessarily wrong the way we did it initially, but you are setting yourself up for confusion in the next step. So now what we can do is we have a double sum. What can we do to handle the expected value of the double sum? We use we can use linearity, right? When in doubt, use linearity. You do not need independence to use linearity. That's one of the things that's so nice about it. So I have the expected value of two sums. This is equal to the sum I goes from 1 to n, the sum j goes from 1 to n, the expected value of ai aj xi minus mu I xj minus mu j. And in fact, if I want to use linearity again, what could I pull out? I could pull out the AIAJ. Bless you. AIAJ is a constant. If I want the expected value of a random variable, bless you, if I multiply it by 5, I just increase the expected value by a factor of 5. So I can pull out the AIAJ. I have the sum I goes from 1 to n. The sum j goes from 1 to n. AIAJ. Now I have the expected value of xi minus mu I, xj minus mu j. Given a value of I, which index j do you want the most? I. If j equals I, then you've got the expected value of xi minus mu I squared. Ooh, what's the expected value of xi minus mu I squared? The variance. So this is the same as the sum I goes from 1 to n, ai squared, I'll do it slowly, the expected value of xi minus mu I squared. And now there's several ways to do it. I have the sum over I and j that are not equal. So one nice way to write this is I can write it as, 2 the sum I less than j. And that would be the expected value of xi minus mu I xj minus mu j. And the reason is if I have a pair of indices that are distinct, say 3 and 5, I also have the pair 5 and 3. Yes?
Are we missing an AI?
Oh, yeah, we're missing, yes. Thank you. So I need to write, sum I less than j, ai, aj. Because if I have the pair 3, 5, I have the pair 5, 3. So I might as well just choose I to be smaller than j and then just double count. Well, the first piece is exactly what we were gunning for. I goes from 1 to n, ai squared variance of xi. Now, if they're independent, what's the expected value of the product? 0. Why? I'm sorry? You're close. So what result can we use? The expected value of a product of independent random variables is... So expected value of a product is the product of the expected values. Well, what's the expected value of xi minus mu I? The expected value of x minus its mean. So, right, so it's going to be 2 sum I less than j, ai, aj, expected value of xi minus mu I, expected value of xj minus mu j. And this is because we're assuming it's independent. Question?
If they're not independent, is that the covariance term?
That's going to be the covariance term, exactly. And so here, if I use linearity of expectation, the expected value of the difference is the difference of the expected values. Right? So if independent, this is 0. This is the expected value of xi minus mu I, which is 0. So all these terms will vanish if they're independent. So if the random variables are independent, then the variance of the sum is related to the sum of the variances. You just have to control with these weights. The problem is there will be many cases where these things are not independent. And so this is technically called the covariance term. We're not going to talk too much about the covariance right now. But over here, this would be the covariance of xi, xj. Why do you think it's called the covariance? What does it look like? Yes?
Just to be precise, is the covariance only the
expected value?
value?
Yes. Because I'm talking about the covariance of the terms xi and xj. That has nothing to do with the a's. What does this covariance look like? It should look like something you've seen. Or can you give me a choice of j where you understand what the covariance is? What would be a good choice of j? I. And so what's the covariance of xi? The variance. So it's just the variance of xi. So this gives you maybe some idea of why they're calling it the covariance. It's how x and y vary together. Okay? So this is going to be an extremely useful result. If we have independence, we don't have to worry about these terms. The formulas become a lot simpler. It's a lot easier to estimate what's going on. Will most of the time variables be independent? No. And that's going to cause a lot of problems. If we just care about the expected value of a sum, do we need things to be independent? No. If we care about the variance, however, we do need things to be independent, or we need some way to calculate the covariances. And so what this means is that for a lot of problems, it's not going to be that hard for us to figure out the average value. But the fluctuations about the average value, that's going to be a lot harder to calculate. Because we need the variances to calculate the fluctuations. Now, there are estimates you can do for the covariances. And so maybe later in the semester I'll talk a little bit about this. If you continue in statistics, you'll do a lot more with covariances. How many of you have taken a stats class? How many of you will take a stats class before you leave Williams? Your hand should have been raised for one of those two cases. Okay? The jobs will be in stats. Okay? It's extremely important, extremely growing field. If you have stats training, especially for those of you who are going off to pure math grad school, if you can teach a stats class, there's a huge plus on your resume. Med schools are close to requiring stats for all incoming students. People will need to teach those classes. Yes?
Can you just go through the step between the second and third ones?
Here to here?
Yeah.
So I break this up into two cases. If j equals I, and if j doesn't equal I. So if j equals I, these two terms are actually the same, and I have their square. And then if j doesn't equal I, then I can use the expected value of a product as the product of the expected values because they're independent. If j equals I is the expected value of the product of the expected values. So if j equals I is the expected value of this product, the product of the expected values. Well, if j equals I have xi minus mu I, xi minus mu I. Are they independent? No. In fact, if the expected value of the product was the product of the expected values, you would have just proven the variance is 0. So nothing changes ever. Okay? The universe would come literally crashing to a halt. Nothing would happen. Okay? Any other questions about this before we get to marriage? I do have, from the very first time I taught this class, one student who has told me he will use this to determine whom he marries. So this is called the marriage or the secretary problem. Not adultery, secretary. There's...
Are they independent?
They're supposed to be. They're supposed to be different spheres of your life. Is there anybody on SMASAP here? No SMASAP? Alright, so we're going to be hiring hopefully at least 2 people in math stats this year. And so we need a way to figure out whom to hire. So there are 2 ways to phrase this. One way is you're trying to determine whom you want to marry. Another way is you're trying to determine whom you want to hire. I am not going to worry about the politically correct way of phrasing this. I will do the standard original phrasing, slightly modified. Alright? I will not ask for a volunteer for this one. Alright? So you have a person who is waiting to get married. And you have a list of candidates. And the candidates, 1, 2, 3, I will make the unreasonable assumption that I actually know how many candidates there are. Okay? Is this a reasonable assumption?
No.
Well, I know how many people there are on the earth. Well, but no, I do not effectively have that many possible candidates for marriage. I will assume I know how many candidates there are. I do not know from the distribution in which they are drawn. Okay? So I do not know what is the most desirable, I do not know what is the least desirable. But as the candidates come in, I can rank them relative to the people I've seen. And I can say better or worse. Okay? And so the candidate comes in, and I look them over, and I decide whether or not I want to either marry them or give them the job, depending on which version of the problem. If I decide to give them the job or to marry them, they will of course say yes. And if you do this as well, of course they will say yes, because of course, you know, you're a Williams student. Who would not want to marry a Williams student or work for a Williams student? What do you think happens if you look the person over and you decide, no?
Do you lose the opportunity?
Yes, they kill themselves. They just cannot imagine life.
I think the same they got married to someone else or took another job.
No. There is no other job. There's no other. Once you say no, because if they took another job, what could happen? The backslide, right? Yeah, they could come back, you could hook up with them again. You know, I want to eliminate that possibility. So the simplest way to make sure this doesn't happen is to either have them kill themselves or to kill them, you know, something along those lines.
So you're sure
This is going to be Exhibit A in a few years when I'm on trial. So once you say no, they are unavailable. All right, we will assume that if somebody is dead, they are not available for marriage. All right, that's another assumption. Okay? I know, a lot of assumptions today. I assumed today was going to be Mo today. I'm not making good assumptions today. All right, so is everybody clear on the rules? They come in one at a time. You can rank them relative to the people you've seen. And once you say no, they are unavailable for all eternity. Yes?
So your answers are either ranking them or just outright saying no?
Well, no, when they come in, you have to say at that moment yes or no.
Okay.
You have to say, and as soon as you say no, they fall on this sword. If you say yes, they marry you or they take the job with you, or maybe both. Okay?
Oh boy.
All right. Does everybody understand the rules of the game? Your goal, and this is a little bit unreasonable, and I'm going to have a student do a good colloquium on this later. Your goal is to marry or to hire the best person. You will consider a complete failure if you do not marry the best, if you do not hire the best. What is a little bit unreasonable about this is if you end up with the second best person or you end up with the worst person, you consider those equal failures. This is not a reasonable assumption. Okay? This simplifies the analysis. A really good twist on the problem is to rank how well you do and to come up with what strategy maximizes the expected value of your partner, the expected value of your candidate. This also introduces the concept of settling. As you get deeper in the list, for those of you who are still young, you may have, well, anyways. All right, so we will assume if you don't get the best, it's a complete failure. It's as bad as getting the worst person. Okay? This is an assumption that needs to be removed, but let's start off here. Can someone give me a strategy where I will get the right person, the best person, at least 1 over n of the time?
Always pick the first person.
Always pick the first person. So we assume the n people are randomly, independently ordered. So you don't have the desirable clump coming in together. Everybody is equally likely to be in every space. So strategy 1, take the first person. Can someone give me another strategy that will win 1 over n of the time?
Take the fifth person.
Take the fifth person. Assuming what?
Assuming that it's greater than
Assuming n is greater than or equal to 5.
Yeah.
Right.
well,
Strategy I, take I if I is less than equal to n. So, if there are 3 people, taking the fifth person is not a good strategy. Okay? In the limit, as n gets very, very large, your probability of getting the best person is really small. Right? Your probability of getting the best person is decaying like 1 over n. How do you think I can come up with a strategy where instead of 1 over n, I can get the best person 1 over square root of n? Nobody thinks I can do that much better. All right. Well,
unless the first person is the absolute best, you can wait until one person is better than one you previously seen.
okay.
And then take that person, because you know that they're the least better than the one you've seen.
So good.
Better than all.
So that's a really good strategy. And I'm going to modify what you said just a little bit. So you said take the first person better than the first person I see. So what we're going to do is we're going to call that strategy S sub k, but rather than taking the first person better than the first person, so sk, take first better than the first k people. So what you're going to do is you're going to look at the first k people, you're going to see who's the best among the first k people, and then the next person you see who's better than that, that's who you marry or hire. And those are very different. Okay. How well do you think this strategy does? Because if the best person is in the first k, you automatically lose. You have no chance of winning if the best person happens to fall in the first k. Do you think I can get over, like, 1 over square root of n? I think only one person thought I could do that well. Alright, so now just, let's see how, it's like, how high do you think I can go? I think I can get 1 over log n.
That's a round where I would expect the bound to be. So
Okay.
I don't-
Okay, so you think I can get up to like 1 over log n, not a positive percent. So in the limit, 100% of the time I will fail. So I can't even get 1%. Okay. So the goal is to beat 1 over log n. Ready? How well do we do? I just like drawing boxes. Okay? Here's K people. These are the first K people we look at, and then we choose the first person better than them. Where do you want the first person better than the... Where do you want the maximum person? Where do you want the best person to be? That would be great if they were there, right? You'd always win. Unfortunately, that's not going to happen. So let's put the best person here. So this is the best. And I'll put them at position... There's lots of different ways of doing the algebra. I'll put it at position M.
Not B.
No. So the question is, do I want to do it as M or M plus 1? Yeah, I'll do it as M plus 1. So we'll put the best person in position M plus 1. Let's calculate the probability we win. Alright? So the probability we win is if I look at the first M people. So here's the first M people. Where do I need the best person of the first M people to live?
In K.
In K. So when best at M, if the best among the, I'm sorry, best at M plus 1, if the best among the first M people is in the first K people. And that happens with what probability? So what's the probability that the best among the first M people is in the first K? K over M. I have M slots, and I have to throw the best among the first M into one of those slots. The probability that they land in the first K is K over M. I have M possibilities, K of them work. Alright? So this is setting us up for conditional probability. So this is a nice way to review a lot of the concepts that we've done this semester right before the exam. So we've calculated the probability. Now let's do the probability we win. So the probability of a win is the sum, and goes from what to what?
K plus 1.
Not K plus 1. The way we're writing it, M goes from K. Because we're assuming the best person is at M plus 1. So the sum starts at K, it goes up to N minus 1. And then its probability we win, given best at M plus 1, times the probability the best is at M plus 1. So we have the sum, M goes from K to N minus 1. The probability we win, given the best is at M plus 1, that's just K over M. And what's the probability that the best is at M plus 1? Just 1 over N, right? The best person is equally likely to be anywhere. Okay? So I can bring out the 1 over N, and I have 1 over N, the sum. Well, let's see, what else can I bring out in this sum? I can bring out K. I have the sum, N goes from K to N minus 1 of 1 over M. Okay, so now it's time to do lots and lots and lots of algebra so we can get a sense of what we want to choose K to be. So the difficulty is, I don't know what the optimal K is. So what class might be useful to find the optimal k? What might I want to use? Calculus. So if I want to use calculus, I want to differentiate. What's the problem if I want to try to differentiate? Yes?
Why are we concerned about the probability of the best person being at n+1? Is it arbitrarily defined?
Well, no, we're assuming that the people are randomly ordered and everybody's equally likely to be in every spot.
Right.
And that it's all independent. So the probability the best person is at n+1 is just going to be 1 over n. They're equally likely to be at every position. When we're doing our partitions, when we're doing our conditional probabilities, the probability that A happens given BI times the probability of BI. That's the formula we're using. So for each of these, we're partitioning the event that we win into all these different ways we can win. We can win with the best person in position 1. We can win with the best person in position 2. We can win with the best person in position 3. And we go through all the different possibilities. Now, if the best person happens to be in one of the first K spots, we lose. And in fact, that's why the sum won't even include that case. All right, so let's estimate this sum. So the probability of a win is going to be k over n, and I'm going to write it as a sum. M goes from 1 to n minus 1 of 1 over m, minus the sum m goes from 1 to k minus 1 of 1 over m. Oh, maybe I should have done it the other way. And so now if I want to estimate the sum, okay, now when I sum 1 over m, what does this look like? So who's seen a sum like 1 over m before? Yes?
Harmonic.
It looks like a harmonic. So this is going to look like the log of n minus 1. It's either plus or minus Euler's constant here. Is it plus or minus? Does anybody remember? Plus or minus Euler's constant plus small. Then I subtract off the log of k minus 1 plus or minus Euler's constant plus small. And what we're using is the sum of 1 over n goes from 1 to n, is approximately the log of n plus or minus some constant plus some really small error to it. This is the harmonic series. So there were two ways to choose where m was. And it turns out we chose the wrong one. Okay? So I was happy with either way that it worked out. If it worked out right, great, we would have wonderful algebra at our disposal. If it works out poorly, I have a chance to talk to you about why some ways are better than others. Notice we have an n minus 1 and a k minus 1. That's a little bit annoying. What would we much rather have than n minus 1? N. What would we much rather have than k minus 1? So here we started the sum where the best one was at m plus 1, and we had m go from k to n minus 1. So we could redo the problem. So change notation. Best is at m. M goes from k plus 1 to n. In that case, we would get the probability of a win is going to be the sum. M goes from k plus 1 to n of, now, before we had k over m, now we have k over m minus 1, right? Times 1 over n. And so if we do that, we'll get k over n, and then we'll have a sum. M goes from k plus 1 to n of 1 over n minus 1. Does that make anything better? Unfortunately, no. The upper value of the sum is still what? It's still n, but when we put it here, we'll have a 1 over n minus 1 term. So no matter what we do, we're actually stuck with bad algebra. Right? oh well. We're stuck with the n minus 1 and the k minus 1. We unfortunately can't fix things by changing what we start m as. Are we starting at the best or one more beyond? Doesn't really matter. At the end of the day, we get the same expression. Alright, so all we have to do is analyze that expression, and we have to determine what's the best value of k to pick. So, if you look at this, the larger k is, the better the probability of winning. But the larger k is, the more we're subtracting off over here. So it's a competing influence. So we want to study probability we win is k over n, and I'm going to do it approximately. The log of n minus the log of k. Am I allowed to do this? If n and k are large, the log of n minus 1 is approximately the log of n. The log of k minus 1 is approximately the log of k. This is a really good approximation. Okay? We're going to look at a large number of people. I mean, if n is 1,000,000, I'm not going to look at just 2 people. So now, what's the log of n minus the log of k? The log of n over k. So consider the function f of x equals the log of x divided by x. This is the same as the log of n over k divided by n over k. I want to figure out where is this function largest. How do I figure out where this function is largest? Take the derivative. So f prime of x, the derivative, oh great, quotient was wonderful. Right? The derivative of log of x is 1 over x times x minus the derivative of x, which is 1 times log of x, divided by x squared. I want that to be equal to 0. So I get 1 minus the log of x equals 0. What is x equal? One minus log of x equals 0. We don't have much time. If we don't do this quickly, you won't know who to marry. We've got 2 minutes. We've got to go fast. What is x equal if I want 1 minus log of x to be 0?
Let's see.
E. The log of e is 1. Right? So it tells us that the best choice is when n over k is about e. Another way of looking at this is this going to be a maximum? Well, let's think. If I go through the algebra, you'll see that f prime of x is increasing if x is less than e, and decreasing if x is greater than e. Or maybe it's the other way. Right. So this is going to be the maximum value. You can look at the derivative here. If x is really small, the derivative is positive. Right? Because you have 1 minus something like this. And then as x becomes larger and larger and larger, the derivative becomes negative. The plot looks something like this. Okay? So just using calculus, we can see that the best choice is we want n over k to be about e. So now it's time to see how well I did. You know, Greg was the only one who thought I could do better than 1 over n. He thought I could get all the way up to 1 over log n, but not much more than that. So we want n over k to be about e, or k is about n over e. So the fraction of the people you look at before you make your choice is about 1 over e of the total. So the probability we win is going to be k over n, the log of n over k. Well, what's k over n? 1 over e. And what's the log of n over k? The probability we win is 1 over e. Not only did I beat 1 over n, not only did I beat 1 over square root of n, not only did I beat 1 over log n, I have a positive percentage. That's over 30%. In fact, it exceeds 33%. I have a better than 1 in 3 chance of finding the best person with all my assumptions. Okay. Now, the big assumption is that I know how many people there are. Okay. We will talk about that, or one of my colloquium students will talk about that. So, I thought in honor of Mountain Day, I was trying to save some fun thing to look at. All right. So you didn't get to climb the mountain, but now next Friday when you climb, Those are your candidates. Okay? Yes.
How does your student intend to implement this? The one who's
So the problem is, it seems to be very difficult to get enough data points on somebody before you decide. You can't really evaluate many people at the same time, so he's going to look at a couple of people, decide whether or not he wants to pursue the relationship.
Decide how many people he would have dated after he
This is one of the big